At ULA, we know what it means to put something on the line. Standing on every launch pad are lives, careers, and hard-earned reputations. For more than 120 countdowns, we've mastered the technology, and we've mustered the fortitude to put our nation's interests, our human connections, and commerce into the heavens. And now it's time to reach even higher. It's time to solve some really tough national security problems. Time to advance human spaceflight. Time to pioneer a backbone for a whole new cislunar economy. That's why we're going to harness the potential of space. Not just for our nation, but for all humanity. So let's continue breaking ground with innovations like Vulcan. Let's uphold our commitments to our national defense. And let's double down on our ambition to be the ones who shape and guide an achievable transformation in space. It's time to lead the way up there so we can help expand what's possible down here. That's why we're ULA, and no one puts more into space.
And thank you, ULA, and that's what Mark was talking about, getting excited just to get things going again. So we're going to close out the day talking about advanced exploration technologies. And our moderator today is Mr. Ron Birk. Ron and I talked about having this panel many weeks ago. Ron is an Associate Principal Director of the Development Directorate within the Aerospace Corporation Civil Systems Group. Ron's done a lot. And a lot of it is in remote sensing, and after reading his resume, I could tell you a lot more, but I'm going to turn over the dais to Ron and let you introduce your panel. Thank you, Ron.
All right, thank you, Chris, for that graciously and mercifully short introduction. And I would like to just take a second to recognize what a fantastic day this has been, and give recognition to Chris and Jim Way and Alan for all of the coordination that they've done. So please join me in recognizing all of their work. I would like to expand the introduction just a bit before going into the panel, just to put in perspective the Aerospace Corporation. So we as a nation have a federally funded research and development center that is focused on the space enterprise. And the Aerospace Corporation operates that center for federal agencies across the government. So we're very pleased to have the opportunity to bring physics and engineering-based solutions and analyses and assessments to support the agencies as needed and when needed. So just sharing that perspective. One of the core functions of the Aerospace Corporation is technology application, and that's a bit of a stage setter for this panel. As Chris said, we wanted to focus the panel on those exploration technologies that are absolutely critical to accomplishing the goals of the Space Policy Directive 1 and getting to the moon and to Mars and beyond. And there are a number of very significant technologies that still need to be developed, but in the interest of time and recognizing that we were at the end of the day, we chose just 4 to really focus on predominantly. And those include autonomous operations of systems, nuclear thermal propulsion, environmentally controlled life support systems, and in-space and on-orbit assembly and manufacturing. So we're going to focus there predominantly. We are so fortunate to have Jim Reuter, who is serving as the Associate Administrator for NASA's Space Technology Mission Directorate, who's leading and administrating a $600 million investment to mature technologies for both science and exploration, including the 4 areas that I've just mentioned: smart autonomy, in-space propulsion, life support systems, in-space assembly and servicing. And with that, Jim, I'd like to turn the floor over to you.
Okay, well, thank you, Ron, and it's a pleasure to be here today. It's been a really enjoyable day. I wish this weather would stick with us the rest of the week. Do we have the pointer, or do we just ask somebody to? Oh, there it is.
There you go.
Thank you. I really enjoyed the previous chart because it includes our tagline of the things we try to do. And that is, we invest in so that we can go, land, live, explore, and then prosper. Recognizing that the things we do, that the investments we make to further our exploration in space really are spent on the ground here. And so when we try to look at ourselves, and we really believe that technology drives exploration, so I'll give you a little bit of an overview and then try to focus on a couple of the areas that you talked about, but the panelists that are coming are specializing in those areas. But for us, the way we think of ourselves is that, first of all, we spark innovation by engaging the brightest minds, both in industry, university, and in our NASA workforce and other government agencies. And that enables exploration and discovery by embracing competition and public-private partnerships and then investing in America. And the way we do so is we look across the entire technology readiness level scale, and with a focus on things. Most of what we'll be talking about here are things that are at what we call the higher TRL, that are ready for demonstrations. But also we maintain a significant amount of our investment in early stage. Our goal, our target is to have about 8% of our budget, which is actually about $760 million, but have about 8% of our budget focused on early stage. And so these are things, whereas our overall portfolio, especially now with SPD1, is focused on especially enabling lunar, and then but our activity is also to keep an eye on Mars and beyond as we do so. And we focus on exploration, but as Thomas just talked about, there's a very strong link between science and human exploration, and we find those things partner well together. And so we focus especially along those lines. And then in the early stage, just for reference of a few things, over our portfolio, we review about 3,000 proposals a year. We make about 700 awards a year. We have partnerships with over 300 universities, 300 university partnerships, grants in over 140 universities. We have about 400 industry partners across our portfolio. Most of them are small, but we have things in the tens of millions and then hundreds of millions even across our portfolio. And then, let's see, and there was one other one. Oh, well. I'm sure it'll come to me at some point. Anyway, so we try to take that portfolio. Oh yeah, the other one was we have about 60 things right now getting ready to go to flight of different projects and stuff. So this chart has been shown before, and I won't belabor it much here, other than to say that as we look towards, especially the investments in the lunar and with an eye towards Mars, then there's the gateway activities. As well as lander activities, and we look at the places where we fit into those as well as to Mars. And so this next chart then is a little bit of an eye chart, but it just says that a sampling of the types of investments we make for those. Communications is a big thing. The solar electric propulsion is part of our goal. Our unit is the unit that's going to be as part of the power propulsion element. And enabling about a 50 kilowatt system. Optical communications, we're doing demonstrations now that are developing for flight. That's a joint with Air Force and with our Human Exploration Mission Directorate. And actually we also just demonstrated a couple of CubeSats. There was the OCSD project that recently is a 1.5 U CubeSat. There were 2 of them, and we demonstrated over 200 megabits per second downlink. We have the ICERA, which is an RF downlink, and it's kind of a consolidated reflector array antenna and solar array system in a way that's effectively no volume lost, and that demonstrated over 1 megabit per second. So Networking, smart autonomous systems are crucial for us. We have things that are in work now for, the Gateway is a resurfacing facility is one of its things. So robotic refueling and assembly of activities is something that's critical for that. And then what I'll do is kind of talk about the lunar surface operations in the next chart. But then as we go to Mars, we're looking at things like terrain relative navigation. We're demonstrating on Mars 2020. We have instrumentation that will help us on landing. We're looking at what we call a lofted program, which is one of the tallest tall poles for going to Mars is to land very large masses. And Mars has got the atmosphere that's just wrong. You know, it's kind of just the opposite of being of Goldilocks, because its atmosphere is thick enough that it causes you problems, but not thick enough to slow you down. So then hypersonic decelerators is something we're doing a demonstration of in low Earth orbit with ULA in a partnership agreement, because that same technology of an inflatable hypersonics can actually also be a large return to mass system for orbit. And then in terms of priorities for us, then when we talk about the Lunar Lander, so what we have done from our part is we look at which technologies can we help enable the human class exploration and landing on the moon, and also then how can we take advantage of the platforms. So we're very excited and a strong part of the Science Mission Directorate what we call the Lander Services, the CLIPS program, because we see it as an opportunity to develop and demonstrate technologies that will feed forward. And so it's a great platform for us, and we're participating in the science calls. The ROSES call is one that's out now for people to propose against, that's mostly for science instruments as well as technology. And then we'll have calls continue as we go out. But what we're also doing is we identified 3 areas that really were the most enabling for us to accomplish the landers that also feed forward to Mars. And the first one is in precision landing. Precision landing and hazard avoidance are a number of technologies that we're in developing, and then we have what we call tipping points. We have partnerships with industry to demonstrate those technologies as well. And then so we have a program that's designed to use the small landers and feed into a mid-sized lander, and then ultimately and demonstrate those systems to feed ultimately to a human class lander, and then also use those as we go to Mars. With that, you need higher computing power than we have standardly available. And one of our technologies that we're developing is one actually with science and with Air Force, and it's on high precision space flight computing is what we call it, but high performance space flight computing. Basically, it's the replacement for a RAD 750 that's been a workhorse for about 15, 20 years from science missions, and it's one that's scalable using today's technologies basically for fault-tolerant architectures. And so this will be our first demonstration of that technology that will feed to exploration as we go forward. Cryofluid management, as we get into larger landers, performance is critical, and long-term storage of cryogenics is something that we're investing very heavily in right now. We have a number of contracts in place with industry, and we've gone through a roadmap for those and identified 25 critical technologies, identified which ones can be demonstrated on the ground, and those that need an orbit demonstration, and we're funding almost all of them right now, basically. And then finally, really one of the critical things to really sustain our presence in lunar space is that we need to be able to survive and operate through the lunar night. The moon is a very threatening, difficult place. It's one of the coldest places. When it's nighttime, it's one of the coldest places in the universe, and when it's daytime, it's one of the hottest places. There is no atmosphere, and it sees those. And so, and then a night lasts 14 days. It's and so that operating is through that really demands that we change the way we think about power generation. There's a number of ways that we could do that, but we recently demonstrated what we call a kilopower nuclear fission reactor at about a 1 kilowatt level. It was a joint project with the Department of Energy, And we demonstrated that and demonstrated its fault tolerance and ability to manage. And right now we're in the process of going through a pre-formulation activity to see about fitting this on a potentially mid-sized lander. With that, then in situ resource utilization, of course, is a critical item as we go forward. And it needs a power source, though, so the two couple well for us to have. And so those three are the primary technologies, but we have a number of other things as well as we go forward. And I'll turn it over then back to you, Ron.
Jim, thank you so much. To Jim's left, we are joined by Dr. Jonathan Cirtain, Vice President for Advanced Technologies with BWX Technologies. Jonathan has advanced the use of machine learning and data analytics for Earth science. He's pioneered imaging of the sun's corona, and he's here today to share progress plans and challenges for developing nuclear thermal propulsion systems. We understand that Jonathan is an avid adventurer, so no doubt he will take us on some exciting journey here.
Well, we'll see. Thank you for that, Ron. So I figured what I would do is, many people really don't know who BWX Technologies is, at least in aerospace, so a bit of a small introduction on our behalf. So we're a pure nuclear company. We only make nuclear reactors and systems for nuclear reactors. We've built about 300 nuclear reactors to date, including the first ones for the Rickover Navy. Just recently, we passed 1 million miles flown in the oceans in service of the nuclear Navy. We have about 6,000 employees scattered over a variety of different locations in the United States and Canada. We also manage an operation in Canada to do a lot of the servicing of the CANDU nuclear fleet. We make fuel for the nuclear Navy, a lot of the research reactors across the Department of Energy complex and for the military, as well as the CANDU in Canada. Little tie into Thomas Zurbuchen from earlier. If ever needed, we also make robotic systems to fly through the containment vessels within the pressurized water, boiling water reactors, so we know how to make semi-autonomous robots that operate in high radiation environment in case anybody ever needs one of those. So, as I said, we've got operations scattered throughout the United States, both for manufacturing of nuclear systems, but we also have a large footprint within the DOE. The DOE has a number of different sites, laboratories, national labs in a variety of different areas, and BWXT has some role in management and operations of those different sites, 14 of those different sites. We also have management operations enterprises with Michoud and Stennis. So BWXT has a fairly long history in space exploration and development systems, starting in 1959 with the Project Mercury. We've developed systems for Orion, the Apollo missions, Skylab, a number of different variants of nuclear thermal propulsion. Our first NTP contract, Jim, was in 1987, so we're really looking forward to that in-space demonstration of that thing at some point in my lifetime. So we've been building NTP designs for a while. We're ready to build an NTP for real. Recently, Jim and STMD awarded us a contract to help develop a nuclear thermal propulsion system, a reactor for an in-space propulsion system in collaboration with Marshall Space Flight Center, Aerojet Rocketdyne, and Dynetics. So we've been working on that for the past several years. Starting
It's gone very well.
And we are very excited about the progress we've made. We recently tested systems in the CFEAT separate effects test setup here at Marshall Space Flight Center, and soon in FY19 we'll further those tests in the entries test setup, and then later in FY19 start some testing of fuel test specimens in the treat reactor at the Idaho National Lab. So we're very excited about the progress we're making and very much look forward to continuing that program. So a little bit about the game-changing development funding we have for NTP. NTP is a highly enriched or a high-assay LEU fueled nuclear reactor. It's designed to output 500 megawatts thermal power using a ceramic metal fuel, CERMET fuel, for eventual manned exploration. The current design for what's called the Copernicus architecture would have 3 such engines that each generate a substantial amount of power. I'll talk about that in just a moment. 19.75 high-assay LEU is non-proliferable nuclear fuel. So this is not something that can be used to make a weapon. However, it has a high energy density, sufficient enough to actually make the type of power necessary to get the thrust and ISP that really do benefit human exploration in lower transit times and launch abort scenarios. So in addition to the design of the reactor and the development of the fuel elements, we're also working with Stennis and STMD for the licensing and design of the ground test system. So we're very honored, pleased, and excited to continue those efforts in FY19. So for those that don't really understand what nuclear thermal propulsion is all about, we thought we'd introduce you very quickly to that. Effectively, propellant is heated by the reactor and expelled and thermally expanded through a nozzle. The low molecular weight of the propellant is directly proportional to specific impulse. So the lowest molecular weight propellant we can choose is hydrogen. It turns out you can use other things, but it lowers the ISP. Hydrogen is by far the best propellant. ISP is directly proportional to the exhaust temperature. So if you can make a fairly exotic reactor, commercial reactors operate at about 600 Kelvin. The one that we've been designing with NASA operates between 25 and 3100 Kelvin. So that's a very different type of metal that you use for the cladding, for the containment of the reactor and its fuel. But the higher you can operate that reactor, the higher you get the ISP. Thermal power is also directly proportional to thrust. So to get to 500 megawatts of thermal, when you design something to 500 megawatts thermal, you get about 100 kilonewtons of thrust. So you take that combination with the high operating temperature and low molecular weight propellant, and you get a 900 second ISP, 35,000 pound thrust system. So in the design, we will use this high-assay LEU fuel, and the amount of uranium that you'll expend over the course of the one Mars transit and back is about 100 grams for the 3 reactors. It's about the size of a marble. So you have a lot of fuel left over in that transit. So this is a highly reusable system, very relevant for the other topics on the panel today. So the last thing here is just our summary. Very excited about the forward work, the progress we've made here at Marshall with the CFEAT tests, our future work with gaseous hydrogen and the entry separate effects tests. Look forward to continuing our progress here and for a soon in-space demonstration of this capability. So thank you very much.
All right. Thank you, Jonathan. All right, and to Jonathan's left, we have Robyn Gatens, the Deputy Director of our International Space Station, and NASA's lead for the maturation of technologies associated with environmental control life support systems. I'm betting that Robyn has never met an ECLIS system that she didn't like, at least the ones that work.
Some that only I like.
Right.
I can vouch for that.
There you go. And particularly the ones that work really well. So Robyn, please.
Thanks, Ron. Yeah, it's great to be here. I've spent 27 years at Marshall Space Flight Center, 6 years at NASA headquarters, so it's like coming home to be back here. Shout out to the students for hanging in. I see more students in the audience than I do, I think, my generation, so thanks for hanging in there with us today. I'm going to talk about the environmental control and life support systems and the challenges that we're facing. Just to set everybody who may not be aware, on the space station today, we have a regenerative life support system that supports our 6 crew. It recycles about 90% of the water, and it recycles a little less than half of the air. So that sounds pretty good, but we do rely on a healthy supply chain from Earth to supply spare parts and makeup consumables, take trash away, and that's our big challenge as we go beyond low Earth orbit. how do we break that supply chain? How do we have a life support system that we can send everything we need for it and it's sustainable? So I've kind of divided this into challenges that we're facing, in low Earth orbit, and then as we go out towards the moon, some new challenges that we're going to be facing, and then on to Mars. Right now, today, we're trying really hard to improve the reliability of our system that we have on space station. The crew time is precious on space station. We like to use all of our crew time as possible to conduct science. We don't want to have the crew doing a lot of maintenance. We have pieces of our life support system that the crew has had to work on a lot. We're also trying to reduce the uncertainty. We calculate something called mean time between failure, and we use that data to project how many spare parts are we going to need of these items to have a successful mission. There's a lot of uncertainty around those calculations. If we had, at the beginning of space station, for example, if we had taken that data and tried to project what we needed to take to Mars, and between the beginning of station and now, 15 years later, flying our life support system, we've reduced that uncertainty to the equivalent of several tons of spares now. We could take that trip to Mars and not have to take as much stuff with us. But it's taken us a really long time to reduce those uncertainties and to gather that data. So that's one big challenge that we're trying to deal with. And then we have our space station. Space station is the perfect test bed for our ECLSS system. It's permanently crewed. We have microgravity. Our fluids act funky when you get them in microgravity versus ground, so we can't always rely on finding problems in a ground test bed. We need an on-orbit test bed. As been talked about earlier, we talk about what's going to happen in LEO, what's the future of the space station, are we going to have commercial space stations afterwards? That's the other hat I wear at headquarters, talking about that policy. For ECLSS, we know we're going to need an ongoing LEO test bed. So because we need a place in microgravity to continue to test our system, it's important for us that we have something after the space station in LEO to continue that testing. So that's one kind of policy challenge that we're facing as well. So we move out towards the moon and the gateway. Now we have a few new challenges that we're trying to think about. With space station, we've launched our system and it's been permanently crewed ever since. We've never had a time where crew haven't been on board to provide the water and breathe the air. At Gateway, it's going to be crew tended, crew going back and forth. So what does that do to the life support system when we have these dormant periods or uncrewed periods? We can't leave dirty water behind. We know it will grow bugs. And potentially the hardware won't work when we go back. So we're having to think about those issues right now and how to design our system for those dormant periods. Along with that, autonomy. So how do we design a system for the gateway that can operate somewhat autonomously when crew is not there? We're not going to have this supply chain. We're going to have a supply chain to the gateway, but not like we have to the space station today. So things like getting rid of trash become even more important, and reducing our logistics needs for the gateway becomes more important. And then finally, dust. We're starting to do missions down to the surface. They're going to be coming back to the gateway. They're going to be dragging in dust. We don't have to deal with that on space station today. So that's a new challenge to our life support system to filter that out, make sure it's not a health hazard for the crew or our hardware. Going beyond the moon out to Mars, now we are really worried about, hopefully we've proven our system But we really are worried about that spares mass that we've got to take with us to Mars. I've said before in forums like this that the key thing that keeps me up at night thinking about this future mission is when we close the door and the crew inside, and what they have is what they have. And if hopefully we've guessed right on what they're going to need, how many spare parts of which kind. But having a robust system is going to be paramount. And along with that, the more closed loop we can get with our life support system, the better. Then we don't have to provide as many consumables. If I had to pick one, robust versus closed loop, I'd rather have a robust system. Closed loop is a bonus. And then finally, this sort of related, we have other folks in our human research working more on the food system, but I put it on here because the food system has a lot of interdependency with the life support system. So food system is a big technology gap. Today, we send like 800 different menu items up to the space station. The crew eats very well. We're not going to be able to do that on a mission to Mars. How do you design a food system that provides the nutrition for the crew and remains nutritionally viable for this long period of time? We're looking at things like a garden kind of pick and eat system that the crew can have some fresh food to supplement their diet. So all of these are kind of our big challenges. And then, so how are we doing this evolution? Today, we're starting with space station. We're already doing this. We're evolving the system we have on the space station today into the system we believe is our deep space exploration ECLSS system. And using station as our test bed to do long-term testing of that system and prove that it is reliable. I'm super excited because on the next flight, the NG-10 launch, we're flying up our double toilet stall. So we're flying next year, we're going to be flying a US commode. Today on space station we have a Russian commode. And we're going to be flying a US commode. And in order to accommodate the two toilets, we're adding a double toilet stall to node 3. That doesn't sound like a big deal, but when you're an ECLSS person, that's a big deal. So we're going to have the stall is going up ahead of the toilet. It's going to be fun for the astronauts to install that guy in node 3. We've got a lot of hardware we're going to be flying next year. We've got one of 3 CO2 removal systems that we're going to be demonstrating. Flying next year, we've got a brine processor that's going to be taking the leftover waste from our urine processor, that 10% of water that we throw away today, and it's going to recover the water from that last 10%. We're going to be demonstrating that. We've got an atmosphere monitor flying next year. So this is a whole lot of stuff about to happen, and we're trying to get all of this hardware evolved on station by around the 2022 timeframe so that we can do this kind of long duration test. From there, like I said before, we're hoping we can transition onto a commercial platform and keep this test bed going in LEO because I want to still have the ability, we're working on new technologies all the time. I'd really have a hard time flying a brand new technology on a deep space mission to Mars without first testing it in LEO. So I want to have a test bed in LEO where we can continue to infuse new technologies and test them. From there, the gateway, we're starting to work on ECLSS concepts for the gateway. Initially, we're probably going to have what we call our short duration ECLSS or more open loop ECLSS, more Orion-like, and then evolve that to our fully regenerative system, hopefully, where we recycle more of the air and the water. And then use that as a proving ground for when we do the trip to Mars. And then we got surface missions that we're looking at. If we do, it depends on if it's an excursion type of mission only. That's going to be our more open loop short duration ECLSS. If we're talking about something like a lunar base, that's going to be more of our regenerative system. So what we're doing in LEO will infuse all of these different mission scenarios going forward. So that's what I had. Thank you.
All right, thank you. Okay, so just again resonating with Jim's mantra of go, land, live. Right, we're stepping right down that path. Explore, we've heard a lot about today, but also the finale is prosper. And so rounding out our panel is Al Tadros, the Vice President of Space Infrastructure for Space Systems Aral. Al's 27 years of experience on 13 missions informs his passion for the nexus between commercial and government capabilities and really leveraging the benefits of commercial capabilities to serve government missions. And that's an important aspect of the sustainable capabilities in space. As we look forward to an increasingly vibrant space economy, Al, we look forward to you sharing with us the challenges of actually physically building things in space. Please.
Great. So the year is 1945, and von Braun has been busily working on rockets and seems to have found time to do an Army study to think about what humans will do once rockets can take them to space. He finishes the study, and this graphic depicts what he comes out with. A toroidal space station that's about 50 meters in diameter, and not only has the concept figured out, but he lays out the eclipse for how this is going to help humans survive. It's going to provide a 1G gravity environment. It's going to have algae that scrubs the air, provides the oxygen. It's going to have water purification system, a power system that concentrates solar light onto mercury to heat in a heat engine. He's got it all figured out down to space taxis to move people around the space station. This is the start of the vision for what are we going to do once we are in space? How are we going to survive and live in space? And this is 20 years before we actually put humans in space. Much of the science fiction, other concepts, growing toroidal space stations grew out of this era and posed the opportunities for us today. I'll take a little side here since half the room are students. I was inspired to be in the aerospace industry by a competition that in the early 80s allowed students to pose experiments for the space shuttle. The student involvement program for a space shuttle allowed not only ideas to be generated, but competitions to be had to identify how you would commercialize. How would you get a sponsor? How would you get funding? How would that experiment have relevance to industry? I won a regional competition in 3 states and came here to Marshall Space Flight Center to present in 1985. Unfortunately, January of '86, this Challenger accident ended that program. If there are any people from Marshall Space Flight Center here that were involved in that program, I'd love to talk to you. But this is the kind of experience that jazzed me, along with others, teachers and other experiences, to go into aerospace engineering. And I'm happy to be back here and talking today. Over the last now 50, 60 years, as we started going into space more and deploying more systems, robotics has been fundamental to our ability to persist in space. Robotics has led the way in many domains. Robotics now have been deployed on Mars, as Thomas has talked about before, in dust environments to drill and sample the environment. They've been used along with humans on the Space Shuttle program to service the Hubble Space Telescope, deploy satellites, and robotics were used to actually assemble with astronauts the International Space Station. Robotics have been part of our space environment and architectures from the beginning. Even today, on a daily basis, the robotics are used for the external maintenance and installation of science payloads and execution of the missions on the outside of Space Station. That is an ongoing activity. Johnson Space Center has control for the robotics. Marshall here does a lot of the payload operations that go on the exterior. This is an ongoing and great proving ground for how we can operate platforms and destinations in preparation for humans during human presence, and after their presence, both in orbit around Earth, Moon, and on the surface of the Moon. So currently, we are fortunate to be working on multiple satellite servicing programs that are using robotics to be able to affect satellites that not only are designed to be serviced, but satellites that are not to be designed to be serviced. This is a NASA program called Restore-L. It's from Jim's group, the Space Technology Mission Directorate, to be able to take robotics, launch them in low Earth orbit, rendezvous and berth with Landsat 7, be able to, what you're seeing here, uncap, unscrew, and then refuel the satellite that was never designed to be fueled. However, it was fueled on the ground. There are tools and processes for fueling it, so the robotics have to be able to do that. Close it up, and then separate it, and demonstrate that you can do that on a reliable basis. That is the start of what we have to be able to do regularly in order to persist in space with humans beyond Earth orbit. The ability to refuel, to resupply, to dock, all these skills that we're going to be demonstrating on Restore-L. Another program that we're working on called RSGS, or Robotic Servicing of Geostationary Satellites, goes a little bit further, but also in a geostationary environment. It actually uses robotics to inspect potentially a damaged satellite, to be able to dock, berth, and repair the satellite, refuel the satellite, add payloads or enhance the satellite, all with satellites that were not designed to be serviced in orbit. So geostationary orbit has about 300 commercial satellites, another 100 or so government satellites. It's a great market for commercial business, and hence DARPA set up a program that's not only technically innovative, but also commercially innovative. And this is the kind of thing that NASA is now looking to do more and more with partnerships to deploy technologies like in-space robotic assembly and manufacturing, not only for their benefit, but then sustained on a commercial basis. So part of this, although you see the robotics, there's a whole ecosystem that has to occur, and access to space is part of that ecosystem in order for satellite in-space assembly and manufacturing to survive. So SSL has been working on the ability to actually deploy small payloads off of commercial satellites in order to resupply satellite servicing vehicles. Geostationary orbit is not quite as easy as putting a dispenser on a launch vehicle. Most of the satellites going there are actually doing their own orbit raising. So we developed a method here to actually take up and deploy payloads from the commercial satellites directly. Another application of robotics and in-space assembly that we are working now is the ability to self-assemble on orbit. So satellites are configured and constrained to fit within a fairing. However, their optimal configuration is probably best done once on orbit rather than constrained to a fairing diameter, the vibration, acoustics, shock. So being able to take robotics up with you, unpackage your deployables, install reflectors, lay out the payload is part of the future architecture. Similarly, robotics that would be used to reconfigure upper stages for future habitats are being worked. Again, this is a program that Jeffrey Manber from NanoRacks talked about a little earlier. We're partnered with them to develop and demonstrate a vehicle called Independence 1, which is an in-space reconfigured upper stage of a launch vehicle. This is not a new idea, but an idea that whose time has come with the robotics and in-space assembly capabilities that are now possible. The architectures go beyond human spaceflight and for future commercial platforms. At SSL, we do a large number of commercial geosatellites. The ability to affect how we build them and how we deploy them and then how we enhance them is something that we're very interested in. Simply being able to reconfigure satellites once on orbit allows for architectures that maybe haven't been looked at or thought about before. This is a self-contained robotic system in an architecture that's very volume efficient in a launch vehicle fairing, deploying what will be a geostationary satellite, communication satellite that looks quite different than traditional satellites right now. So in-space robotic manufacturing and assembly, lots of robotics capabilities that are being developed right now. There's aspects of this that include additive manufacturing and other manufacturing techniques that are being worked by a number of people and are in part of those demonstrations that I think are quite exciting and increase the possibility of what we can do with in-space robotic manufacturing and assembly. I want to talk briefly about solar electric propulsion, which plays into this because of the efficiency of moving from space to space. Large volumes of equipment, supplies, and especially non-time sensitive materials. Right now in the commercial world, we're deploying electric propulsion, a second generation of electric propulsion that allows up to 30% more payload capacity per launch vehicle. And that's a substantial improvement over time. It's hard to get that kind of improvement from launch vehicles alone or other methods. The same kind of technology is being used for government programs, civil space, and others. Jim Reuter talked about the investment they're doing in high-power electric propulsion that's going to play into the gateway, as well as deep space operations. Right now, 6 kilowatts is fairly standard in commercial systems. There are 12 kilowatt thrusters that NASA is investing in, and visions for much higher both power systems and propulsion systems. So this portrays a bit of what the potential is in the future, starting in the 40s of what space stations might look like with a necessity to be able to assemble in orbit. We believe that the future is very feasible in achieving these kind of platforms using in-space manufacturing and assembly. Thanks.
All right, thank you, Al. Okay, and least we believe that these kinds of technologies don't come to fruition. In the early 90s, I had the good fortune of leading a program for NASA called the Commercial Remote Sensing Program, and we were advancing remote sensing technologies at that point that were at the TRL 3 and 4 level. And today we take those kinds of capabilities for granted with Digital Globe and Planet Labs and Spire having commercial satellites on orbit. So, you know, these technologies do come to pass. Questions, please.
What will be the course of action for testing out the kilopower reactor and any larger nuclear reactors meant for space and planet habitation?
I'm sorry. I want to make sure I heard your question because I didn't quite hear it. You were asking how would we test the kilopower reactor?
Yes.
What we recently did back in March, we were at the Nevada National Security Test Site and with DOE, a joint project there. And then we had tested in one of their facilities, basically, for this. One of the reasons we picked the size reactor we did was really to make one that's simple and straightforward and fits in their facilities. And so this was a good size that demonstrates the capabilities. It also fits there. And we were able to demonstrate it through 28 hours of operations, basically that we put faults into the system and watched it react and stuff. And it did extremely well and matched all performances. So as we go forward and we're doing our formulation plan of how would we test it on a lander, there would be the natural Nevada, there would be certainly more nuclear testing that will be on facilities like that, whether it's DOE or DOD. And then there'll be others that would be just the normal processing of integrating into a system.
I guess me.
Yeah, Frank?
Frank Slazer, obviously AIA. Interesting that a satellite manufacturing company is coming up with a system to service, refuel, and repurpose existing assets that are out there. What do you see in the long term? Because the last few years, geosynchronous satellite orders have been dropping a little bit worldwide. What do you think the impact of that technology will be on the demand for geosatellites in the future as well as for launch services?
Yeah, very good question. So the commercial geostationary satellite business has been around for about 35 years. It only survived through innovation. Over the last 35 years, it's been a dramatic change in technologies that are used, in frequencies and coverage and service provided, right? So lithium-ion batteries, right, alone, electric propulsion, dramatic change in capabilities and performance. The necessity to develop and innovate is that geostationary satellites are not a market on their own. They're part of a telecommunications industry that is very quickly changing. To stay relevant, that's the necessity. So we don't see this as a disruption any more than we saw Ka band as a disruption to C band or KU band. It's a natural progression. It's a cost efficiency that has to be achieved in order to make it relevant in the telecommunications market. And we've been fortunate along the way to be part of the technology innovators in that commercial business. So right now, our corporate family includes MDA in Canada and our Pasadena group, which has been building most of the robotics that showed earlier. Of course, MDA provided the robotics for station through the CSA contribution, Canadian Space Agency contribution. So the existence of the robotics and the existence of our commercial satellite market allow us to put those two together in order to innovate the commercial market. Hopefully that answers your question.
And I'll add, since your Dragonfly is a technology that we're partnering with you on, that's the in-orbit assembly part is actually can be transformative on the capabilities that you can introduce.
Right. The satellite which you saw self-assemble reflectors is something we're doing in partnership with NASA and has relevance, cross-cutting relevance, hence it's in STMD, has huge potential because as you get larger Ka reflectors, you can provide smaller spot beam, more frequency reuse, which provides higher throughput commercial satellites. Price point goes down. It's all a plus. Developing and maturing and then sustaining that allows us to provide that kind of capability back to NASA and other government agencies. And we appreciate DARPA before that and NASA's partnership in investing and deploying that kind of capability.
All right, so I suppose my question is more directed in terms of nuclear thermal development, so I guess it's more to John and Jim, but everyone feel free to chime in. I guess as someone who's worked around the nuclear thermal propulsion systems, those have been in development, I know you mentioned NERVA, since the 70s. And I suppose, at least from my knowledge, a lot of the challenges there are non-technical in terms of certain international treaties and such and so forth. So I suppose what my question is how are you guys, because it sounds like you had a very useful and well test on the ground here, but how are we going to test that into space, and what's your plan of attack for maybe some of the non-technical challenges you're going to have to face there?
Well, that's a great question. I hope one day to know the answer. The reality is building these reactors is something that the U.S. government and BWXT and others in industry have the capability to do. Fitting them within a proper fairing, understanding their use case in space, that's design work, that's engineering work, that's some development work that can be done and will be done. Solving the regulatory and policy implications for launching fission-based systems into space is a challenge that the government's also attacking as well. So the National Space Council, OSTP, and members of the OSTP FFRDC group are working with NASA, with DoD to understand what the insert process should be and what revisions should be considered to make this something that's doable with the proper safety in place, but without the regulatory impediments that may prevent those activities. Radioisotope launches have occurred on, I don't know, 30 some odd, is that right? 30 some odd science missions over the course of, starting with Voyager. So MMRTGs and related technologies like that have been launched, but it's an egregious process. I think the OSTP crew that's working on it would tell you that if you tried to determine a single path forward, it looks just like photon transfer from the radiative environment of the sun all the way out through the convection zone and into the solar wind. It's a random walk. So making that thing work in a reliable, effective way so that the dollars being spent are dollars being prepared or dollars being applied to making sure that it's safe without making it a regulatory burden is very important. So I think having a demonstration mission drive through that, whether that's an on-surface power system like kilopower or an in-space propulsion system, really is going to be the use case. It's going to help the government figure out its way through that regulatory thing, as well as solving the remaining technical challenges that'll make this a useful technology as humans expand to live and work in space. Thank you for the question.
I would say that nuclear, both power and propulsion, is really transformative of how we go forward. And if there's one thing we can do is get there a whole lot faster to be important. And what I would say is the environment is right now to be introducing nuclear systems beyond the radioisotope systems. And in some ways, those are easier to get through the system because they can be controlled so that they're safe during the actual launch process. So, but the environment is good on the regulatory side as well. And as Jonathan said, there's a team working that right now that's OSTP and Space Council, and we're contributing to try to look through of how we get through that regulatory burden. And there's nothing like a flight that would help force that.
Hi.
And a launch date.
What's your launch date?
As soon as he will fund it.
It's a partnership.
I'll pay for that later.
Hi, my question would be also addressed to Jonathan. Your answer already addressed part of my question, but I have some more on the technical side because liquid hydrogen boil-off is definitely a question to think about if you want to use hydrogen for nuclear thermal propulsion. So I was wondering if it's within the scope of your company to do this trade studies on the benefits of nuclear thermal propulsion based on the fact that it does have boil-off and the requirements of radiation shielding, and also whether the use of ISRU potentially on the lunar surface would change your decision-making process in terms of what fuels to use for NTP.
Thank you for that question. Cryogenic fluid management is another initiative within STMD that Jim's organization is funding heavily. Blue Origin and several other companies recently received awards to study those. So it's not a BWXT thing. We make nuclear reactors and that's it. So, but for these systems to be useful in space, we need to have a sustainable fuel supply for the propellant, not for the nuclear fuel to power the reactor. So those cryogenic fluid management solutions have come a long way. Marshall Space Flight Center, Dynetics, and others here locally, as well as Blue Origin and others within the industry, have made a lot of progress in making sure that boil-off in passive systems is something that can be well controlled when the propellant is not in use, and then understanding how to flow through nozzles and valves and use pumps and turbo machinery to actuate the turbo machinery and operate the reactor. For something on planet to operate in a closed loop system, active cycle systems are a longer term solution. These are Brayton cycle type systems. The benefit of kilopower was to demonstrate a non-active system, Stirling engines. These are difficult to build, but NASA figured out, and Glenn figured out a way to do it, and they were very effective at transferring the heat out of the reactor in a safe way. All the transients that they created made that system very reliable and safe to operate. But to get the energy levels above 30, 40 kilowatts electric, you got to go to some active system. So Brayton cycle systems or some other closed loop system is going to be necessary for larger power solutions. I think NASA's done studies and their architectures indicate, at least in the near term, maybe they don't need the higher level power requirements for some of the shorter duration exploration missions on the moon. However, longer duration missions and the types of heat and electricity that are going to be required probably require these active solutions. Doesn't change the fuel. High assay LEU can be used in either instance. It's just a matter of sizing the reactor's total performance, the amount of megawatts thermal that you would get, how much fuel you have in it. As a consequence, how quickly you burn that fuel up is really the use case. So you can use a high SALU in either instance. You wouldn't want to go to enrichments much lower than that because the energy density drops off pretty quickly. You don't really need to go to enrichments much higher than that. It does lower the total weight, but it's not necessarily the case that you have to do that with new advances in manufacturing that allow you to put all the U-235 in the positions that you need it and not have to pack it all in there because of the enrichment.
I guess my question was more in terms of as opposed to
If we may, in the interest of time, thank you very much for the excellent questions and encourage the follow-on afterwards for sure. But let us all thank the panel for the outstanding contribution.